Hello, everyone. The presentation you're about to see is part of a research project for class CNT3122 Sensors for the Internet of Things with Professor Dr. Chaparro. Today, we will be highlighting the key points of the article. The Internet of Disposable Things will be made of paper and plastic sensors, published on IEEE.org. We are Carlos Corraz and Boris Navarro.
All right, so before explaining what IoDT is, I would like to comment quickly on where it stems from. So, the Internet of Things, IoT, is revolutionizing the way we interact with the world by connecting billions of devices to the Internet, enabling automation, real time data collection, and smart decision making. From smart homes and wearable devices like wearable health monitors to industrial automation and precision agriculture, IoT has permeated nearly every sector, as we can see on the diagram on screen. The projected growth for IoT is staggering as well, with the number of connected devices increasing from 27 billion in 2017 to an estimate of 125 billion by 2030. However, not all IoT devices are designed for long term use. The Internet of Disposable Things is a new concept that focuses on developing low cost, temporary sensors for applications such as food packaging, medical diagnostics, and environmental monitoring. Unlike traditional IoT devices that are built to last, IoDT sensors are meant to be used for short durations and then discarded, raising critical questions about cost, scalability, and environmental impact. So that being said, I would like to discuss the challenges of IoDT. And despite the promise of the Internet of Disposable Things, the biggest challenge is cost. Most IoT sensors today are based on silicon microelectromechanical systems, MEMS. This technology is very expensive to manufacture, making it unsustainable for disposable applications. The cost of a sensor must be driven down significantly to make disposable IoT viable. And I'll give an example. To sell a 1 millimeter square sensor for a penny, so $0.01, the total manufacturing cost cannot exceed $0.007. This allows for a 30% profit margin, meaning the manufacturer would only collect $0.003 in profit per sensor. Sensor manufacturing follows the rule of thumb where the MEMS chip accounts for 30% of the total cost, while the remaining 70% comes from packaging, testing, and readout electronics and calibration. This means the MEMS chip alone must cost just $0.002 to fit within the budget. However, even before considering the cost of fabrication, the silicon materials itself account for 20% of the total MEMS chip cost, leaving only $0.0004 available for raw silicon. In other words, for silicon based MEMS technology to achieve a zero point zero 0.01 price point, the cost of silicon would need to be reduced to one fifth of its current cost, which is not feasible given today's production methods. This cost barrier makes silicon an impractical choice for disposable IoT sensors, driving the need for alternative materials. So, what's the solution? Paper and plastic sensors. To overcome the cost of disposability challenges of traditional IoT sensors, researchers are shifting towards using paper and plastic based sensors as an alternative to build silicon. These materials are not only cheaper to produce but also biodegradable, reducing electronic waste and making them ideal for disposable applications. Paper and plastic sensors offer several advantages, actually. They are significantly lower in cost, as they can be manufactured using inexpensive and scalable printing techniques. Unlike rigid silicon sensors, they are flexible, allowing them to conform to various surfaces such as food packaging, human skin, or textiles. Most importantly, they are biodegradable, meaning they can be broken down naturally over time without leaving harmful electronic waste. These make them attractive solutions for short term applications like food safety, medical diagnostics, and smart packaging, where sustainability is a key concern. Now that we know the solutions to this challenge, where can we apply the Internet of Disposable Things? Well, disposable IoT sensors have a wide range of applications, particularly in industries where single use or temporary monitoring is required. One major area is food packaging, where sensors can track the freshness of perishable goods. For example, researchers have developed sensors that can detect the spoilage of meat products, such as a sausage freshness sensor that changes color when the product is no longer safe to eat. In healthcare, biodegradable mechanical implants are being explored for monitoring conditions inside the body without requiring removal. These sensors can dissolve after their intended use, reducing the need for additional procedures. Environmental monitoring is another important application where disposable sensors can track air and water quality before naturally degrading, eliminating the risk of environmental contamination. In the textile industry, for example, smart clothing embedded with temporary sensors can provide real time health data for athletes or patients, offering insights into hydration levels, muscle strain, or body temperature, without, of course, the long term electronic waste concerns. Now, I would like to dive deep into each of these material based sensors. I will start with paper based sensors. Paper based sensors have emerged as a promising solution for disposable IoT due to the low cost that we discussed previously. It's also very flexible and biodegradable. Researchers at Clarkson University have developed paper based food spoilage detection sensors that change color based on the freshness of perishable items, as I mentioned before, and they can also rely on chemical reactions that indicate spoilage, providing an expensive way to monitor food safety in real time. Now, in the medical field, Harvard University has pioneered paper based diagnostic sensors, which are being used to detect diseases such as malaria, HIV, and COVID 19. These sensors function similarly to at home pregnancy tests using paper strips coated with um, reagents that react to the presence of specific biomarkers. The main advantage of paper based sensors is that they can be bendable, foldable, and fully biodegradable, allowing for easy disposal after their use. They can also be printed using scalable manufacturing techniques, further reducing production costs and making them accessible for widespread use. Now, following to this, plastic based sensors. So, plastic based sensors provide another viable alternative to silicon, offering flexibility and biodegradability while being more durable than paper based sensors. Researchers at the University of Pennsylvania have developed biodegradable pressure sensors that can be used in wearable electronics and medical implants as well. Now, these sensors are made from biodegradable polymers such as PLGA, which stands for polylactic co-glycolic acid, PVA, which is polyvinyl alcohol, and PCl, which is a polycaprolactone. These materials are already widely used in medical applications, such as dissolvable sutures, meaning that they are safe for temporary implants and wearable devices. Plastic-based sensors provide an ideal balance between cost, durability, and sustainability, making them suitable for applications like flexible medical patches, environmental sensors, and smart textiles. While they do not degrade as quickly as paper, they still break down naturally over time, minimizing their environmental impact compared to traditional electronics. Now, I want to talk about power sources because this is one of the key challenges in developing fully disposable IoT devices, which is just finding sustainable power sources that align with the principles of biodegradability. The issue is that batteries are not suitable for this type of systems that we're developing. So, researchers at the University of Pennsylvania are developing biodegradable batteries that provide temporary power before dissolving safely. Another innovative approach comes from Sonny Bringhamton, where scientists are now exploring paper based bacterial batteries that generate electricity using bacteria. These batteries harness biochemical reactions to produce power, offering a sustainable energy source for short term IoT applications. In the future, self powered disposable sensors could be developed to harvest energy from ambient sources such as body heat and kinetic energy from motion, light, eliminating the need for traditional batteries altogether. These advancements will be crucial in ensuring that disposable IoT sensors remain both functional and environmentally responsible.
The shift to paper and plastic based sensors for the Internet of Disposable Things, IoDT, presents unique manufacturing challenges. The goal is to adapt existing technologies to produce these new sensors cost effectively and at scale. Adapting existing technologies like paper printing press could be essential, crucial, like for screen printing as well, or roll-to-roll plastic manufacturing. I will explain it in detail right now. Uh, Paper printing press, could be repurposed to print conductive inks and other materials needed for paper-based sensors. In the same way, screen printing as a versatile method can be used to deposit various materials on both paper and plastic substrates. Roll to roll plastic manufacturing, uh, understood as the manufacturing process used to produce flexible and continuous materials by printing, coating, or processing them as they move through a series of rollers, um, could be adapted to produce large volumes of plastic based sensors efficiently. The Next Flex Center in San Jose, California, is at the forefront of developing flexible hybrid electronics. This approach combines the best of both worlds. Thin silicon components provide the necessary computational power and advanced functionality. And flexible substrates, paper and plastic materials, offer flexibility, biodegradability, and lower costs. This hybrid approach allows for the creation of sensors that are both high performing and suitable for disposable applications. The author of the article believes that the future of IODT sensor manufacturing is likely to shift towards a distributed model. What does that mean? It means decentralized production. Instead of large centralized factories, manufacturing could occur in smaller, more localized facilities. Therefore, home-based sensor fabrication may be possible and maybe even encouraged. As technologies nowadays become more flexible, there's potential for individual to create simple sensors at home, similar to how 3D printing, as you can see in the picture, has evolved. This distributed model could lead to more customized sensors, reduced transportation costs, and faster innovation cycles. The article also points out that the sensor market is expected to split in two main segments: high performance sensors, which will remain on traditional silicon platforms that can be used or will be used for applications requiring complex computations or high precision, and the simple high volume IoT sensors, which will transition to plastic paper substrates, which are ideal for disposable applications and large scale deployment. This bifurcation allows for optimized solutions in both high performance and high volume, low cost applications, driving the growth of the IoDT market. Summing up, the Internet of Disposable Things represents a transformative shift in IoT sensor technology, driven by emerging low-cost, flexible substrate methods. This innovation enables the production of sensors on paper and plastic materials, drastically reducing costs while manufacturing functionalities. These advancements address critical challenges in disposable applications where affordability and scalability are paramount. This has been our presentation. Thank you for watching. If you have any questions, please feel free to post them on the forum. Thank you and have a great day.